Hi, this is Mrs. Westmoreland, and this is a method for calculating limiting and excess reactants in solution stoichiometry using more of a table method. So this is exercise 11 out of your solution stoichiometry notes, and we're looking at aqueous solutions of sodium sulfate and lead 2 nitrate being mixed to form a precipitate of lead 2 sulfate. So we want to know the mass of the lead 2 sulfate formed when we have 1.25 liters of 0.05 molarity lead nitrate and 2 liters of 0.025 molarity sodium sulfate. And we also want to calculate the molarity of any ions that are in solution after the reaction is complete. So because I have measured quantities, liters and molarity of both of my reactants, that's the way I know this is a limiting reactant problem. And so first, as always with stoichiometry, I need a balanced chemical equation. So I've labeled that here as reaction because sometimes this method is called a Rice table. So the R stands for reaction. So I write the equations, the formulas for my reactants, and we're told there that those are both aqueous solutions. Solubility rules would also tell us they would be aqueous, since sodium is always soluble and nitrate is also always soluble. Then we're also told one of the products. We're told that the lead sulfate precipitates, and so that product is labeled as a solid. So since this is a precipitation reaction, that is a type of double replacement reaction in which the ions switch partners in the products. So since the lead is now paired up with the sulfate ion, that means the sodium from the first compound is going to pair up with the nitrate from the second compound to make our other product. And since sodium is +1 and nitrate is -1, the formula of that product is NaNO3. And we know that's aqueous because of the solubility rules. And we need a 2 in front of it just to balance the equation and for the law of conservation of mass. So the I of Rice table stands for initial, and so what I'm doing here in that I is I'm calculating the moles of each reactant using the volume and the molarity. So if we think of capital M, molarity, in its sort of fraction style ratio format, what 0.0250 capital M means is 0.0250 moles of solute for every 1 liter of solution. And so if I multiply the volume in liters times that fraction style ratio of the molarity, I get the moles of sodium sulfate. I do the same thing with the information about the lead nitrate. I get the moles of lead nitrate. I also write down as an initial concentration or initial number of moles of my product, 0. And really I'm only paying attention to the lead sulfate product because that's what I'm asked about in the problem. And I'm kind of going to think about the sodium nitrate in a slightly different way. I'm not going to think about it in the table because those are spectator ions. Whatever number of moles are formed in the reaction is really the same as I'm going to have to begin with because nothing changes about those ions. And I just think it's easier to think about their initial number of moles rather than their final number of moles. So the C of Rice table stands for change, and really that's where I factor in the mole ratio. So for every 1 mole of sodium sulfate that is used up, I'm also going to use up at the same time 1 mole of lead nitrate because they react in a 1-to-1 mole ratio. And I'm going to form 1 mole of the lead sulfate. So essentially I'm using X to represent kind of my mole ratio. And so whatever X moles of the reactants are used up, I'm going to form that same number of moles of the product. Now if I had coefficients in front of any of these, I would have to use 2x if there was a 2 coefficient. So if I was considering this sodium sulfate, I would have to put a 2x plus 2x in this area of my change for the sodium sulfate because of that coefficient of 2. So then when I look at that and I see that they react in a 1-to-1 mole ratio, for every mole of sodium sulfate, I'm going to use 1 mole of lead nitrate. I can see I have more lead nitrate. So that tells me that the sodium sulfate is going to be the limiting reactant. And so by definition, the limiting reactant is completely used up. So I can put its ending number of moles as 0 and sort of label it as my limiting reactant. And then that also lets me know that what my X is equal to. Because if I start with 0.05 moles and I end up with 0 and my change is minus X, then that X is equal to 0.05 moles. And so I can fill that in as being the value for X for the lead nitrate and also for the lead sulfate. So 0.0625 minus 0.05 is 0.0125 left over, and 0 plus 0.05 is 0.05 for the lead sulfate moles. So now I've identified which reactant is my limiting and which reactant is my excess, and I sort of know how many moles of my excess reactant remains after the reaction goes to completion. I also know how many moles of my product are formed. So the first part of the question asks, how many grams of that precipitate? So since I know, I've just figured out that 0.05 moles of lead sulfate were formed by the reaction, I can just use a gram to mole conversion using the molar mass of lead sulfate to figure out how many grams of the precipitate is formed. So I don't have to calculate it 2 times like I do in some other methodologies of doing limiting reactant. Once I've already figured out using the table which one is my limiting reactant, then I only have to use the limiting reactant to determine how many grams of my product can be formed. So now we're going to move on to thinking about which ions remain in the solution and what their molarities are. So I've drawn a net ionic particle level diagram here. And so our first reactant, sodium sulfate, is an aqueous solution of an ionic compound, which means the best representation in a particle diagram of that sodium sulfate is as ions. So I'm writing them as separate, freely floating ions in that first beaker. Notice that I have 2 sodium ions for every 1 sulfate ion in this beaker to mimic the ratio that I have in my chemical formula. Same is true of the lead nitrate reactant. It is also an aqueous solution of an ionic compound that not only dissolves but also dissociates into ions. And so I've shown that as ions floating around separately in the beaker. And again, I have the ratio in the beaker that is proportional to the ratio in the chemical formula. So 1 lead for every 2 nitrates. So once the reaction takes place, I know that the lead sulfate is my precipitate. And so I draw that settled to the bottom of the beaker and kind of joined together in its solid form. And I know that my sodium and my nitrate ions are spectator ions. They remain unchanged by the reaction. They are floating around before the reaction, and they're also floating around after the reaction. So I write those spectator ions in the beaker, in the solution, suspended in the liquid. And then I also know that because the lead nitrate was my excess reactant, the excess ion in the net ionic equation is really going to be the lead ion. So I'm going to have still a lot of sodium and nitrate ions because they're spectators left in the beaker, but I also have some excess lead, so I've drawn that suspended in the beaker as well. And I just wrote the net ionic equation so we could really sort of identify not only what the limiting reactant is, but really what the limiting ion is in the net ionic. So since the sodium sulfate was the limiting reactant, that means really the sulfate ion completely disappears and is totally in the precipitate at the bottom of the beaker. But because the lead nitrate is the excess reactant, there will still be some of the lead 2+ ion that isn't bonded with the sulfate at the bottom of the beaker. It's the excess ion. So by definition, if it's limiting, then the concentration after the reaction is equal to 0. To find the concentration of the lead ion, the excess ion, I take the moles at the end and divide by the total volume of the two solutions that combine. So going back to my table, the moles at the end of the lead ion is this number of moles right here. And the total solution volume is the sum of the 2 liters of this and the 1.25 liters of the other solution that are now combined in the same beaker. So I divide for the molarity of the concentration of the lead 2+ ion after the reaction occurs, the moles at the end that I got from the table, divided by the total solution volume to get that excess ion's molarity. Now for the sodium and the nitrate, I think of those as being unchanged by the reaction. So really I'm looking for the moles of sodium at the beginning of the reaction, which is the same as what it is at the end of the reaction, because nothing changes about the moles of sodium. They're unchanged by the reaction. Same is true of the nitrate. So I'm really looking at the moles at the beginning of the reaction divided by the new total solution volume when you combine the 2 beakers into one. So where am I finding these numbers for moles at the beginning? Well, I'm going back to my table, and I know how many moles of sodium sulfate I have at the beginning of the reaction. I also know how many moles of lead nitrate I have at the beginning of the reaction. But I have to factor in these chemical formulas and these subscripts in the compound to get the moles of the particular ion. So remember how I wrote 2 NAs for every 1 SO4 here. That's a mole ratio. 2 sodiums for every 1 lead, that's also a mole ratio. So to get the moles at the beginning of the sodium, I take the moles of the compound and then use the fact that there are 2 moles of sodium ions for every 1 mole of sodium sulfate to get the moles of sodium. And then I divide the moles of sodium by the total solution volume to get that molarity of the sodium ion. Same is true of the sodium nitrate. I find the moles at the beginning by taking the moles of the compound in which it is found, the lead nitrate, multiplying by the subscript 2 moles of sodium for every 1 mole of lead nitrate to get the moles of nitrate that are in that beaker, and then divide that by the new solution volume, the 3.25 liters, to get its molarity. And the reason I can do this is because these are spectator ions, and whatever the initial number of moles is for those ions are going to be the same as the final number of moles. And it's just easier than adding together the ending excess plus the ending product to find the moles of the spectator ions. Just think about them as being unchanged from their beginning number of moles. So good luck practicing this, and I'll see you in class next time.